Hello. Right, we've had a week off. Once again from your homework. At least everybody's on the same homeworks finally. So you should all have technically done some biology in the week. And I have ready here the three different possible things that many of you may have had. So whatever people in year nine did, year 10, and then year E. Oh, that's not year, that's the wrong one. Um, anyway, I'll figure this out. Year nine, year 10, and year 11. That's not right. So if you have anything from any of those places, then start asking first. And then I am going to be doing later on, depending on the questions, a specific chemistry topic relating to reversible reactions, which will be more applicable for the year 10 and 11s, but you are welcome to stay regardless. Uh, I think also those of you who are in year 11, in the back of your homework booklet, you might have had the answers. I think we start doing that at some point where we just give you the answers because it makes more sense given that you have some exams coming up. Right, got some questions. So, the question about the website, da, da, da. If you could just send us an email, I don't know who that is, firstly. So if you could send us an email just mentioning that, then I'll set it up with an email address and password if I haven't done already. Um, for the English homework, what questions were we supposed to attempt? I don't even know. Just do one of them at least. Um, yeah. There's usually a longer writing task. The more you do, the more we'll mark basically with that English homework. So I can't remember what it was now. Yeah, usually just as much as possible for the English section. I actually genuinely can't remember what it was. Um, so yeah, just do one of the longer questions towards the end. Right. Someone has asked questions 1B, 5 to 8 from the year 10. Fine, I'll do that. Year 9, question 1I, really? Okay. And can you go through question 2 in the year 11 book, please? Yeah, I'll do that. Okay, so I'm going to start with the year 9 stuff. Move that out of the way, which hopefully is this. Um, question 1I. I mean, is that question 1I? I don't know what you mean by question 1I. That question 1I down here. Right, okay, that one. Right, okay, big question. Okay, good. Let's start with this because this might have been repeated in one of the other homeworks as well. I'll do that first. Um, Displaying IV characters in the graph, things with Arista. Whoever that is, just so you know, the anonymous attendee, if you could, if it's possible, if you could just rejig your name, so that I know who it actually is, it's helpful. Um, the one about the IV graphs and the graph. Yeah, and I'll talk about that as well. It's quite relatively straightforward. Um, okay, let me start with this one if there's no other question in the year nine. Oh, is it? Oh, hello. Yes, I'll do that. That's fine. Sure. So, yeah, the electricity IV graphs, that's fine. I'll do that. They take a little bit of understanding, but I'll get through it. Right, a question like this, relevant for everybody, very much so. It says here how the villi are adapted for efficient absorption of sugar molecules. 4 marks. Okay. Firstly, there are some things that you should eat. The whole point of the villi, just so you understand very quickly, is that if this is some food, right, while it's being digested, once it is small enough, what happens is that it's absorbed by these things into the blood. So the blood is flowing around here. So once it's small enough, this absorbs them, and that's great. They're in the small intestine, just for clarification, on the walls of the small intestine. Right. And then you have to use this question to answer how they are adapted for the efficient absorption. So what is it? What makes them special that allows them to quickly take up lots and lots of food molecules? So firstly, you should say that they have thin walls. Having thin walls is basically anywhere that diffusion happens, we have thin walls essentially. And you want to say something like, I'm not looking at the mark scheme for this one, but um, that thin walls reduce the distance for diffusion. And remember, the question says explain, so you have to say a little bit more. You can't just say thin walls. You need to then explain why thin walls result in faster diffusion. So it's a bit more when you get these explain questions, but it's good for you to see them early. Um, you could also say that they have because there's so many of these, they have a very large surface area. So there's a lot, whilst only two of them are drawn, there are lots and lots of these. And so having a large surface area, again, how do you explain why that makes it efficient absorption of sugar in this case, but any food? It is because having a large surface area essentially means that we maximize diffusion. You can get lots of diffusion taking place at the same time if there's a large surface area. You could also say, because it's labeled, the mitochondria, and actually you could say a bit more, there's microvilli, which means that the surface area is even bigger. Okay, and then these mitochondria, this is a little bit more technical, but the other thing that happens here, so let me just do this. Diffusion is when food or anything moves from a large to a or high to a low concentration. So high to low concentration like that, it moves in. Great. However, what if there was like a little bit more food left over there? And we also wanted that to come across. Now, the problem that we have here is that there's a low concentration there and a high concentration there. You may remember from your knowledge of cell transport that things can move from a low to a high concentration by a process of active transport. And in that situation, we would need to use active transport to take up as much food as we possibly can. But active transport requires energy to happen. This doesn't just happen automatically. We sort of have to force it to happen. So it requires energy from respiration. Where else does energy come from? It comes from the process of respiration. Where does respiration happen inside a cell? Inside the mitochondria. They are responsible for it. So the fact that this is labeled mitochondria, you are supposed to understand. I mean, you may not need it for all 4 marks, but you are supposed to understand that what the mitochondria do is, so you can say that these are adapted because they have lots of mitochondria, which can release energy from respiration um, for when active transport is needed. Probably don't need all of these points. I'm just giving a bit more detail than necessary. Um, oh, can others see my shared screen at the moment? I just want to make sure that I'm not being crazy. Um, it seems like it shared it. It might be something at your end, tomorrow, but if someone just says yes, if they can see my screen. Yeah, okay, fine. I think it's something that's at your end, unfortunately. But yeah, I mean, yeah, okay. Um, fine, right. Anyway, that is that kind of question. How are villi adapted for efficient absorption of sugar molecules? That's essentially the sort of things that you could say from the diagram. So the things that you should know are that villi have thin walls, which means that there's a large surface area. I think most people should be able to say those two things. But remember, if you get a question about explaining, you should say a little bit more about each point. So thin walls means there is a shorter distance for diffusion. If you're trying to diffuse across a thin wall, that's much easier than if you're trying to diffuse across a thick wall all the way across. Um, so that's essentially what that is asking for. I think that's it from that particular. Nobody else has said anything specifically from that. Um, and then I can move on to the 10 bits. Someone's going to come back and ask me an iron question now. Um, okay. So somebody has asked for questions 1B and then 5 to 8. That seems reasonable. Um, question 1B. Um, so don't know where this has come from suddenly. It is important that the nervous system. Okay, right. This might be a bit tricky because you might not have covered much of this, but it's important that the nervous system can detect stimuli. Right. A stimulus is essentially a change in your environment. So, for example, if it's getting a bit hot suddenly, that is a change in the environment. Or if somebody throws a ball towards your face, that would be a change in the environment, right? And we only are able to respond to those things. Like, for example, if somebody did throw something at your head, then the only reason you can respond to it and try and get your head out of the way is because you see it. And so these receptors, the nervous system basically has ways of detecting what's going on around us. I mean, fairly obvious ways, like you can see or hear or feel things. And what and they are it's important so that we can then respond or react to the surroundings. So we can, by detecting a stimulus like something thrown at you, you are able to respond to it, right? You wouldn't be able to respond to something if you're looking the other way and somebody throws something at you, you can't respond to it unless you see it coming. So it is important that the nervous system can detect these things to be able to respond or react um, to the surroundings. And the benefit of being able to react to these surroundings is that we can avoid danger or prevent harm to the body. That should be enough for a couple of marks there. Um, somebody else is saying I can't see my shared screen at all. I'm not entirely sure why. If completely in doubt, if you visit, I'm not even sure this is going to work, but let me just check something. I was going to say you can go to YouTube and I'll be on there, incredibly. Um, um, okay, if you go to It's feels really weird. This I'm watching myself do this. All right, YouTube, Sexual Success UK. On that, I promise you that you can um, watch this, and I can see my screen literally being shared at the moment. It might be a little bit behind where I am here, but technically it works. So I can see it literally on my phone right now. Um, so let me close that because it's weird. Um, the only disadvantage of that is that questions you have to ask on here because I don't respond to that bit. So that was that, right? Question 5 to 8, I think, was the other thing that you said. Questions 5 to 8. Okay. Oh, right. We have here a question that says, in an investigation, 4 groups of athletes were studied. The maximum rate of oxygen consumption for each athlete was measured, and the mean for each group was calculated. The athletes then ran 10-mile races, and the mean of the best time was calculated for each group. Here are the results. So let me say that slowly and properly. We have a group of athletes. We have calculated their rate of oxygen consumption, which is how much oxygen they can take in per minute. And then what we've done is made them run a race, and we've timed how long it's taken. And you would generally, as I assume, agree that if somebody can take in more oxygen, then they should be able to run faster because more oxygen means more respiration, means more energy released, and therefore a faster race time. And we can see that this kind of works because that number for this group is the biggest, and that group has got the best race time. The worst group is Group D in terms of how much oxygen they take in, and their race time is the longest. So that ties up. What is the relationship? Well, what I just said, essentially, which is that the higher the rate of oxygen consumption, the shorter the time taken to complete, or you can say the faster the time. Okay, so the higher the rate of oxygen consumption, just say what this, just rewrite what that says here. The lower the time taken to complete the race. So you have to spend a moment, look at the table, and figure that out. So I think I've just suggested the explanation, right? Which is so this tells you how quickly oxygen is taken into the blood. Okay, so the faster oxygen is taken in, so I'm going to put arrows here, the greater the amount of oxygen taken in, or the faster it's taken in, the faster respiration can take place, the faster energy can be released. Always link these things together: oxygen, respiration, energy. It is just the mark schemes, that's all they do. The faster energy can be released into the muscle, and if the more energy that can be released, the faster you can run. Okay, so more oxygen around your body, more respiration, more energy released, faster you can run. Splendid. Um, 5 to 8. Oh, okay, right. Question 6. A student breathed out into an empty breathing bag 5 times. Okay. After breathing out 5 times, the volume of air in the bag was measured. The volume was 3,000 centimeters cubed. Okay. The air the student breathed in would contain more something than the air the student breathed out. That's got to be oxygen, because we breathe in more oxygen than anything else, right? And the air the student breathed out would contain more carbon dioxide than the air the student breathed in. Just to be clear, when you do breathe in oxygen, it is not the only thing you are breathing in, because the air is a mixture of lots of different things. So you are probably definitely breathing in some carbon dioxide or some nitrogen or whatever. But the majority of what you're breathing in is oxygen. Similarly, when you breathe out, it's probably not just carbon dioxide. There will be some oxygen that is sort of lingering there and some water vapor and stuff, other stuff, but there'll be more carbon dioxide breathed out than what you breathe in, definitely. Um, the student then did some exercise for 2 minutes. The volume breathed out in 5 breaths was again measured. The time, this time, there was 9,000 centimeters cubed of air in the bag. Well, if you exercise for 2 minutes, what happens to your breathing? You breathe deeper breaths, don't you? It's like you've got more air coming out each time because you go much more. So the effect of exercise on breathing surely is that it results in deeper breaths would be enough, I think. Or you can say more air per breath. It's a bit of you have to be very precise about it. You can't just say it makes it faster. I don't think that's quite enough. You need to be very clear that you're now breathing out more air in every breath. And that's why this number has gone up. It was only 5,000 before when you're just breathing normally. But in now it's now 9,000. So every breath has got more air coming out. Name the chemical process that releases energy: respiration. Um, and name the substances produced by this process. Respiration is glucose plus oxygen gives carbon dioxide plus water. That's not the simple equation. The names of the products are therefore carbon dioxide and water. If you see a question that says name the products, then write their names. Don't put CO2 and H2O. Explain as fully as you can why this process has to take place more rapidly during exercise. Well, during exercise, what do we need more of in order to be able to exercise? We need more energy. Okay, so more energy is needed during exercise. And if more energy is needed, well, why do we need more energy? Sorry, we need more energy because there's more, I suppose, because the muscles are working harder, or more muscle activity would be sufficient. Okay, so the question is, why this process of respiration has to take place more quickly during exercise. It's basically because we need more energy. But it's 2 marks. You have to say a bit more, like because your muscles are working harder. Um, I will just do this quite quickly. Does this have a formula in it? No, it doesn't. It says calculate the heart output for this person during exercise. You should be able to figure out. Let me just open up a calculator. See, if I was looking at this question in an exam and I wasn't entirely sure what to do and I hadn't read it properly, then I might just look at these numbers and go, okay, it's 72 and then it's 75. And I might just go, what happens if I times those two together? Oh, it gives me 5,400, which logically means that to fill out the next column, we do the same thing. 165 times 120, which is 19,800. What's actually happening here, should you wish to care, is that this is telling you your heart rate every minute. So that's the number of beats in 1 minute. And this is telling you that with each beat, how much blood is being pumped. So if you wanted to know how much blood is being pumped every minute, then it's the number of beats times how much blood each beat sends. Okay. And so that's why we times them together. So during exercise, your heart rate is higher, as you know. And also, because your heart is pumping harder, not just faster, but each pump is harder, more blood is being pumped from every beat. And so we get a lot more blood exiting the heart every minute when you're exercising. We probably have to explain that in a minute. Anyway, I've done that question. During exercise, more oxygen is carried to the working muscles. Explain why this is helpful. Same question, really. If you get more oxygen to your muscles, it means that you can do more respiration or a faster respiration, something like that, which means that you can release more energy. That would be enough for 2 marks. You could, if you want to understand the better, even more detailed version of this, by getting more oxygen. Well, if you're exercising and you run out of oxygen, you should remember what happens. We resort to anaerobic respiration for a little while, which means that we get some energy without providing the oxygen, but it produces this thing called lactic acid, which is not good. It hurts and it means that we can only exercise for a little bit longer. So ideally, what we want to do is delay anaerobic respiration for as long as possible. And we would do that if we can get more oxygen quickly around our body. So the fitter you are, the more you do that, which means you resort to anaerobic respiration later because you don't need to, because you can get loads of oxygen around your body really fast, which means that you can keep going for longer. And that's simply that. Give 2 other changes in the body that help to increase the amount of oxygen delivered to the working muscles during exercise. Okay, well, more oxygen is carried. The other 2 changes, I think, are in the table here. The 2 changes that occur during exercise are that we get an increased oh, is it coming? Maybe we can't use those 2 from before. Anyway, we have an increased breathing rate. So don't we breathe harder during exercise so we can get more oxygen in and around our body? That helps us during exercise. And you could say not only that we are breathing faster, but each breath is deeper. Do you see what I mean? Like, so there's 2 different things there. Okay, so faster breathing and deeper breathing are 2 different things. Okay, and number 8, lastly, on this one, just well, I'll do this exercise for everybody in case you didn't have this done the other day. But I always like to show, I did this earlier today, but if they are the lungs, and this is, let's say, the rest of the body down here, B, then what you should be able to do is what I'm about to do now. See if somebody asks a question. Arteries dilate to let more. So yes, you can. I didn't give you every single point there, but yes, the arteries dilating is also a correct answer to that previous question. You could also say that the blood it gets diverted from elsewhere. The blood that is going all around your body, if you're exercising, we send more of it to your muscles so that you can exercise for longer. There are other things. Yes. What I'm about to do now, this little exercise, is important if you can recreate this yourself. It is very good. So we breathe in oxygen into our lungs here. The oxygen then goes into the blood, and the blood flows to the heart, and it enters this way. Okay, this side of the heart. That's where it goes in, and it moves down, and then it is pumped out of this side of the heart. Let's continue some arrows. This is called the aorta that it's leaving from, and it goes all around to the rest of the body. When it reaches the rest of the body, that's everywhere, the oxygen moves out of the blood into our cells where they can be used to get energy. And then the cells give the blood back some carbon dioxide because that is the waste product of respiration that they no longer want. The blood then continues its journey, but this time it is carrying carbon dioxide. We call this deoxygenated blood, as opposed to on the other side, we had oxygenated blood. This blood then goes in back into the heart, but we now use the other side of the heart. It goes in that way, and it is then pumped out of this side. This is called the pulmonary artery, and it goes back to the lungs where we breathe out the carbon dioxide, and we start the whole thing again. That little cycle, or the circulatory system, is a very important part. Right, so that was that. And that covers, oh, and there's a bit more on this question 8. Which blood vessel carries deoxygenated blood away from the heart to the lungs? Well, if you've done this correctly, then you can see the blue is deoxygenated blood. From the heart to the lungs is B, and that would be the answer. The natural, this thing is like a 1 mark question, try and remember it. It is the right atrium where we have these things called pacemaker cells. It's only ever going to be worth a mark. Right. And then digitalis is a drug that originates from something called foxgloves, from what I remember. There's only 2 of these that you ever need to remember, certainly at AQA, which is the aspirin comes from something called willow, and this thing called digitalis, which is helpful for heart conditions, comes from something called foxgloves. By something, I mean these are names of plants, so they come from a specific plant. Right. Oh, this question 8 is really long. I might not do the last bit of this because it's very similar to the previous question I did. Um, and I think you might have done this in class. I'm not going to do that question. You can try it yourself. Right, because I've already kind of explained the concept of it. Right, a couple of people have come back from the previous one, so I'm just going to possibly have a look at what questions they're asking and decide if I want to do them. And so in here, there was a question 9 to I. Explain why pH affects enzyme activity is the question here. It's because what you're supposed to know is enzymes, the way they work is they have this thing called an active site. That is the shape into which the food molecule fits. So if you want to explain why, and what happens if it's too acidic or if it's the wrong pH, the shape of that active site changes, which means the food can no longer fit in it. So this enzymes work because the food perfectly fits. It's like a glove, right? It fits into the shape of the active site. If the shape of the active site changes, which can happen at the wrong temperature or the wrong pH, then the enzyme no longer fits it perfectly and it doesn't digest it properly. So what you want to say here is that if the pH is wrong, it changes the shape of the active site. So the food type, the proper word for that is the substrate, no longer fits. It's like a lock and key, but with the lock shape changing, so the key doesn't fit anymore, essentially. Okay, that was that. 3C, somebody has mentioned, I'll see how long this is. Oh, yeah, good. This one is easy to get this wrong. The question says, what type of blood vessel is F? Now, most people would probably recognize that G is an artery because the one that has the small lumen and a really thick wall is an artery. And then often these two can look quite similar, except there's usually a clue. The fact that they've said this is 1 cell thick, the walls of the capillaries are really thin, 1 cell thick, which makes that a capillary, which means by elimination almost, you can see that that one has to be a vein. Yeah. Um, a stent gets fitted to an artery. I think that's fair enough. Um, and then reasonably difficult, but how does a stent help to prevent a heart attack? What a stent does is it helps to fix when you have a blockage, which means that it keeps your artery open. So when you've had a blockage, what it does is it goes in and opens it back up. And by opening it back up, why are we opening it back up? It's to allow the blood to flow through. It happens to be the blood that supplies oxygen to the heart. Um, okay, let me have a look at this next one. Um, I mean, I literally just told you the answer to this question, therefore I'm not going to answer it. Um, although, and then question 9 to F. Where in the digestion might the two protease enzymes be produced? Okay, I'm going to make do a quick table. This is very important for everybody in terms of the three enzymes: amylase, protease, lipase. What again? This is the kind of thing that you want to. If you just sit there bored, right? You want to try and recreate this table yourself. Amylase is an enzyme that digests starch into sugar or glucose. Okay, protease digests protein into amino acids. Lipase digests fat or lipids into fatty acids and glycerol. I won't write that down. The other thing that you want to write down here is where these enzymes are produced in the digestive system. All three enzymes are produced by the small intestine and the pancreas. So that's a nice, easy thing to do to recreate this. And then you should also know that there's two additional things. Amylase is also produced in the salivary glands, and protease is also produced in the stomach. And if you have done that, often a lot of these questions become really, really easy. Like, where might these protease enzymes be produced? So we've got small intestine and pancreas here. And so that, oh, actually, that's a good point. I might have missed a question here. Oh, yeah, sorry. These two enzymes. Okay. This relates to this table, which is there's two enzymes here. One of them is really good in acidic conditions. The stomach happens to be acidic, which means that that has got to be enzyme X. It's got to be that answer to this question. Um, Stomach and small intestine. We make sure that is correct. Yeah, it is. And then someone mentioned 6C. Have I done 6C? I think I've done 6C. No, I haven't. Um, Two ways the composition of blood changes as it flows through the vessels labeled X. Again, you probably should know this, I'm being honest with you. How does the composition of the blood change as it goes through the lungs? Well, if there's blood here going to the lungs, the reason it's going to the lungs is it's carrying carbon dioxide at the moment. Okay. Now, what it does with that carbon dioxide is it lets it out and it goes into the lungs and we breathe it out. At the same time, what happens then when we breathe in? Oxygen goes into the blood. So if the question then says, give two ways in which the composition of the blood changes as it flows through the lungs, basically, you want to say that the amount of oxygen in it increases and the amount of carbon dioxide in it decreases because it lets go of the carbon dioxide so we can breathe it out and it brings in the oxygen. So there you go. Right, here we go. The reason for the Zoom meeting being on YouTube is because it saves it there afterwards. That was the benefit for you guys. I don't look at it. It's just that it automatically ends up there. So it means that you can access it afterwards, should you wish to. Right. The That's it. That's the questions. Right. So 6C, yeah, no, 2F. Right. I think I've answered all the questions anybody asked me, as far as I can tell. Please tell me um, if I haven't. Right. Which means that what I'm going to do next. Why is the heart a double pump? Good question. Um, Let me do that now. So there's two ways of answering that question. You could mention the fact that one side of it pumps oxygenated blood and the other side of it pumps deoxygenated blood. that is effectively what's going on here. But I'm just going to redo this diagram quickly. The one I said that you should be able to do. Lungs, heart, blood, body even. Okay, we breathe in oxygen. It goes into our lungs. We breathe it into the lungs, and then the oxygenated blood is pumped to the heart. That is oxygenated blood. Then the heart pumps the oxygenated blood all around the body. Okay. When it goes all around the body, it effectively gives oxygen to our cells and carbon dioxide is given to the blood. That deoxygenated blood then comes back to the heart, and now this side of the heart pumps it to the lungs. So you see how one side of the heart is pumping blood to the lungs, whereas the other side, if we just highlight this, that side of the heart is pumping blood to the lungs. This side of the heart is pumping blood all around the body. That would answer the question in terms of why it's a double pump, because it pumps it in two different ways, right? One side of it pumps to the lungs, the other side pumps it to the rest of the body. There you go. And that is that particular that's how I answer the double pump thing. Hopefully that makes sense. Another way of doing this, by the way, there's a few different answers to that question. You could also say that there is one circuit which pumps the blood between the lungs and the heart. You can consider that as one circuit, and another circuit pumps between the heart and the rest of the body. So there's your double pump. You see what I mean? There's one pump connecting the heart and the lungs, and one connecting the heart to the rest of the body. The two most recent questions have been maths related. Now, you guys are on, I mean, those of you who are in Newcastle at least, are on holiday next week. I will arrange an additional thing where we specifically do some maths, probably during the day on one of the days that you're on holiday. So next week is the week when everybody's on holiday. It's a bit complicated because in some cities you're on holiday now, and in other cities you're on holiday next week. So I will during the day, during the Easter holidays, I will arrange some additional time where I can. We do these intensive courses as well, so it has to be around that. But I will do that. I won't do the maths question specifically been asked today because I need to get through something else that somebody has pre-asked me beforehand, and I'm doing it in order of priority. So in that sense, I want to move on to those things. Even though I prefer to do maths, I'll be honest with you, I prefer to, but I can't right now. So the next question, I want to do the question about the physics IV graph quickly, and then I'll move on to the chemistry thing that I said, which was to do with reversible reactions and equilibria, which is a reasonably complicated topic. Oh, there was a question too in the year 11 booklet. I'm so sorry. I'm so sorry. No, somebody asked me that. I missed it. I don't know where it is now. There. Question two. Right. Okay. This is going to be a reasonably complicated question. So bear with me. Okay. LDL is one form of cholesterol found in the blood. People with a high concentration of LDL in their blood may be treated with drugs called statins. You may remember statins is a heart treatment which helps to thin the blood or reduce the amount of cholesterol, which means that you're less likely to have this issue of blockages in your coronary artery. A high concentration of LDL cholesterol in the blood, that's what I just said, may result in an increased risk of heart and circulatory diseases. The graph shows the effects of the treatment of one person with 4 different statins, A, B, C, and D, over a period of 8 years. The arrows show when each new treatment was started. So this shows the concentration of LDL. LDL is this cholesterol stuff in the blood. Now, I have no idea what's going on here. Right, so we started with A, with whatever treatment A is. That seems to have no significant increase, at least well, no significant decrease anyway. We've actually increased slightly the amount of cholesterol in our blood. Then we took B, and then it went up loads, so B didn't do much. But the combination of A and B, which is what we started taking here, resulted in quite a big decrease in our cholesterol. The combination of A and C, which we started now, it doesn't seem safe to do all this. It resulted in an increase in our blood cholesterol. Then we started taking D, and D resulted in a significant decrease in our blood cholesterol. So I'm just monitoring what it says on the graph here. So each treatment was continued until the next one was started. So you stop doing one and started the next one. So this sort of tells you what each thing does. Compare the effectiveness of this for 4 marks of the 5 different treatments in reducing the risk of heart and circulatory disease. So I would immediately say that and A, B, and A and C, none of them are very good at reducing the risk of heart diseases because with A, the amount of cholesterol went up, which is more likely to increase our risk of heart and circulatory disease, right? The cholesterol went up. When we had just B, it also went up. And when we had A and C, it also went up. So I'm just looking at the graph to see what caused it to go up. So I would say all 3 of these are ineffective because they actually increase the amount of LDL, whatever that is. Okay, so that's that bit done. Then I would move on to saying that A and B together, though, is effective because it resulted in a drop, and I probably put some numbers in here, a drop from about whatever that is, 135 down to below 90, right? So I actually mentioned some numbers here. Explain that we went from 135 down to 90. Great. And I would also then say that D is also very effective because what did D do? It resulted in our cholesterol dropping from whatever that is to whatever that is. And that should be enough for the 4 marks. I'm not looking at the mark scheme here. It says A and B is the most effective. D is the most effective, or D is effective. And neither A and B alone are effective. You can't tell. Another good actually point, which you could have said here for the 4th mark, is that, in fact, no, I've done it. That is 4 marks. If you said all of that, you'll be great. Oh, and that was it. I didn't realize that was the only question. Okay, I thought there was more. Okay, fine. There's also a talking counter to understand. I forgot the name, where you're told, for example, what mass of okay, yeah, great. Yeah, well, let's do that. I will literally do the exact question that you've just asked me. Even though we've made up numbers here. Okay, so I'll just do that question now that somebody's asked me. So I'm moving on to, no, I want to do that in a second. Let me do the physics and then we'll go on to chemistry. I want to do this in my head. Right. So one of the physics questions was IV characteristics in the graph. Okay. So in physics, I'm going to do 2 of them. Okay. I want to do the bulb and the diode. Okay. So an IV graph in physics is a graph that looks like this. Okay, where it shows what happens to the current of a component as you change the voltage. Now, the reason people don't understand this, in my view, is probably because they don't really get current and voltage properly. So voltage is the driving force that pushes the charge around the circuit. So imagine this is a wire. A wire is full of charged particles, which are very specifically from chemistry, they are the electrons that carry the charge through the wire, right? When you things conduct electricity. So imagine they're just sitting there at the moment. They're not doing anything. What I need to create a flow of charge is to push them with something, and that is where a battery usually comes in. A battery provides that driving force or the voltage, which pushes this charge around the circuit. So let me just complete my circuit. Okay, so now that this battery is here, this charge starts to flow around the circuit, round and round and round. And current is a measure of the rate of flow of charge, which basically means how fast this charge is flowing around the circuit, okay, how fast it's going. Now, logically, if I'm pushing something, the harder I push it, the faster it should go. In other words, the bigger my voltage, which is the push, the faster this should flow around the circuit. So logically speaking, any IV graph should look a little bit like this, right? Because as voltage increases, current should increase. That seems normal. Because as I'm pushing harder, it's going faster. Current is how fast the charge is flowing around the circuit. So ideally, the starting point should be to understand that that is what an IV graph, in theory, should always look like. Because it should just be a straight line, really. As one increases, the other increases. But it's not a straight line. Because for some components unfortunately, as the current gets really high, so as this starts flowing around the circuit really, really quickly, right, the temperature of the component starts to increase. Things start to get hotter when the current is quite high. And for many components, as they get hotter, their resistance starts to increase. Now, resistance I've not mentioned so far. It is a third variable in a circuit, which is anything that slows down this current. So this is going round and round and round. If there's some resistance in the circuit, it slows the current down. Okay. So I think of it a bit like a speed bump. It slows it down a bit. And if now let's focus on a bulb, right? And there's the bulb. The IV graph for a bulb initially does what we said we expect it to do, which is it's just initially a straight line. However, so as the voltage increases, current increases. However, as the current gets quite high, as I said, what starts to happen to a lot of components as the current increases, the temperature starts to increase. And we know this for a bulb, right? I've got a massive light in front of me right now. If the light bulb, if you touch it, it gets hotter. And so we know it gets hotter as the current, as it gets brighter. So the temperature starts to increase. Now, as the temperature starts to increase, the resistance automatically starts to increase, which means that instead of the current going as quickly as it, would have done, it now starts to not increase as quickly. Okay, so it starts to tail off a little bit. So it should continue in a straight line like that, but because it's getting warmer, the resistance is slowing the current down, so it doesn't increase as much as you would expect it to increase. And that's why it looks like that. And then it also just goes the other way because we have in this topic or in this graph, we have negative directions, which means that something can flow the opposite way, and then we get negative value. So it does that in the negative direction, but then it does exactly the same thing as the current gets too high in the negative direction. So an IV graph for a bulb is like this elongated S shape, and you have to be able to explain it like I just did, which is initially as voltage increases, current increases. That's why it's a straight line here. Then as the current gets higher, the temperature starts to increase. As the temperature increases, the resistance increases, and so the current doesn't increase as much, and that's why we get this tailing off at the end of it. The other IV graph that I'm going to mention is a diode. A diode, its circuit symbol, God, is something like, I want to say that, hopefully. There's a line here somewhere. I think that's it. A diode is a component that only allows the current to flow in one direction. So if this current is flowing this way, the diode is sort of pointing to the right, that will be fine. It will allow it through, no problem. If it, let's see what the undo button does here. Yeah, if it was trying to go the other way, it would not let it through. So it only allows the current to flow if it's flowing in the correct direction. That's what a diode does. Now, the way it does that is by having a very high resistance in one direction, but a very low resistance if it's coming in the other direction. Because remember what resistance does? It slows down the current, and if it's big enough, it will just completely stop the current. So the graph for a diode looks, I'll tell you what it looks like first, and I'll explain it. It looks like that, which means that over here it's doing what you expect it to do. So as voltage increases, current increases. But that's because everything's going in the right direction. If we end up with a negative voltage, that just means it's going in the opposite direction. But in the opposite direction, it doesn't allow it through, which is why we don't get any current. Our current stays at zero. Otherwise, the graph should look a bit like it did for the bulb, like it should go that way. So we'd get some values for current, but we don't get any values for current because we're going the wrong way, because we're in the negative part of the graph. That's why it looks like that for a diode, and that's why it looks like that for a bulb. Right, that covers that bit of the physics. Hopefully that makes sense. But again, if you want to ask on Saturday about that a bit more, feel free. All right, one chemistry question before I move on to the thing that, apologies, that was asked early, which is, so the topic, by the way, that you're asking me about is quantitative chemistry and its mass calculations within that. So I'm going to literally do the exact example that you just said to me, which is what mass of aluminium chloride is produced when 13.5 grams of aluminium. Oh, God. Right. That's not the question. Anyway, that's not this can't this is the problem with this. This is not the topic that you're actually asking me about. But I want to change what you've asked me. So I'll tell you what you've asked me. It's not quite the same as what you mean. When 13.5 grams of aluminium reacts with 42.6 grams of chlorine. Okay, let me explain why this can't be the question that you're actually asking me. Okay, because if I write down the equation for this reaction, it'll be aluminium plus chlorine gives aluminium chloride, which is aluminium's in group. Oh crap, group B. I think that's it. AlCl3, I think. Sorry, I need to check the periodic table really quickly. Um, somebody has asked me another question. Okay, this question. I don't think this can be the question your teacher made up. I'll just tell you why in a second. Unless you are telling me that this is exactly the same question. If it is, I'm surprised. So I'll tell you what the answer is to this question in a second. Okay. Um, let me just double check the periodic table. Oh, right. Oh, thanks for the equation. I was looking it up. 2Al plus 3Cl2 gives 2AlCl3. Okay, fine. The thing is, I don't think this can be the question. I'll just tell you why, unless I'm missing something really obvious. If I said to you what mass of aluminium chloride is produced when 13.5 grams of aluminium reacts with 42.6 grams of chlorine, the answer's these two added up. And this is why I don't think this can be the question. Because this is how, so I know the kind of question you're talking about, but I don't think this is it. So I think you need to just double check because I think that the answer to this question is 13.5 plus 42.6, which is 56.1, because that's how chemistry works. There's something called conservation of mass, which is the amount of mass on the left-hand side equals the mass on the right-hand side. The way this question is usually asked is, for example, you know what? No, never mind. This is not quite the question. I'll do it. I've figured it out. So, in principle, that's what happens. Okay. If exactly this much, I think the wording of the question is going to be a bit different, but if exactly this much reacted with exactly this much, then the answer would be 56.1. But I don't think that's what's going to happen in this question because this is quite a tricky question. Okay. So, the idea of this is that one of these two things doesn't fully react. Okay. One of them is called a limiting reactant. So I've seen one question like this in a GCSE paper not that long ago, but they made it a little bit easier than what you made it here, which is where they said you have to identify that one of them's a limiting reactant, which means that one of them runs out. So not all of this 13.5 and 42.6 would react. If all of this reacted with all of this, then the answer to this question is 56.1 grams. There is no debate about it. But if it turns out that only, I don't know, less of one of these two reacts, then you're going to get less of this and it gets a bit more complicated. And I think that's what we have to do here. So I'll just begin this question. So, um, sorry, I have to keep opening up the periodic table everywhere. Okay, sorry, I was getting the numbers because aluminium's mass number I need, which is 27, fluorine's is 35.5, and that is probably it. Okay, what I'm going to do now, what you have to do in most of these questions, if you're not sure what to do, is you have to convert. Um, yeah, it will be a limiting reaction question, yes. Right, so the what I'm going to do is I'm going to convert both of these to moles. The formula for moles is mass in grams over mR. Okay. And so the MR of aluminium is 27. So this is 13.5 divided by 27. The MR of Cl2 is two lots of 35.5, which is 71. So I've got 13.5 divided by 27, which means that I've got half a mole. Um, And over there, I've got 42.6 divided by 71, which means I've got 0.6 moles. Okay, now what we have here is a 2 to 3 ratio, which means that if I've got 2 moles of aluminium, I would need 3 moles of chlorine. This gets a bit funny at this point, but what we need to figure out is which of these two would run out first. Well, you can sort of tell that, look, it's just well, not just because it's less, but because this is a 1.5 ratio. Okay, 2 to 3 is a 1.5 ratio, which means that if I've got 2 moles of this, it reacts with 3 moles of this. If I have 0.5 moles of this, then it would react with 0.75 moles of the chlorine. So 0.5 moles of aluminium should react with 0.75 moles of chlorine, but I've only got 0.6 moles of chlorine, which means that this must be the limiting reactant. Let me just make sure that makes sense. Yeah, okay. This means that because I've got less of this than what I actually need to take part in this reaction, this is the limiting reactant. Okay. Um, wait, I'm going to make this right. Which one's going to run out first here? So 0.5 moles of that. I'm just making sure which one's the limiting reactant. So that is 0.5 moles. Yeah, that is the limiting reactant. Sorry, I was overthinking it. So we've because there's less of this than actually what would take part in this reaction. Um, because we should be able to react 0.5 moles of this with 0.75 moles of that. The fact that we've only got 0.6 of this suggests that this is the limiting reactant. There's not enough of this, basically. So because that's the limiting reactant, it means that when you redo this calculation, not all of this 13.5 grams will react. You see what I mean? Because of this 0.5 moles, it would react with 0.75 moles there, but we don't have enough. So we're not going to use up all of this 13.5 grams, basically. So not all of that will react. And so what we do is we basically do this question, ignoring this, and going, well, if we have only 42.6 grams of this, how will this work? And so we kind of can restart this and say that I've got 0.6 moles of this. I think it was 0.6, wasn't it? Sorry, that took ages for that. Sorry. 0.6 moles of that. And the question is, how much of this will we make if we've only got 0.6 moles of this? Well, because this is now a 3:2 ratio, you could basically go, well, that means the amount here is 2/3 of, which is actually going to be the same, isn't it? It's going to be 0.4. That means we're going to make 0.4 moles of aluminium chloride. And now to turn this back into grams, you multiply this by the MR of aluminium chloride, which you would have to work out. It's going to be 27 plus 35.5 times 3. So 27 plus 35. This is just to be clear, this is a very much a higher level topic, for those of you wondering. 27 plus 35.5 times 3, but not a triple science only topic, I should add. It is in combined. 133.5. And if you multiply 0.4 by that, that will turn it back into grams. I think the answer, having done this very quickly, is 53.4 grams, which wasn't the same as what I said earlier. Earlier, I said 42.6 plus 13.5. So earlier, when I first instinctively looked at this, I said that the answer should just be the two numbers added together, which makes 56.1. But it's not. It's slightly less. And the reason it's slightly less is because not all of this 13.5 grams would have reacted. This is a limiting reactant question. 133.5 times 2. No, you don't have to do that. There's a couple of ways to do this question, right? You don't do that because if you had done that, you would have got an answer that was way too big. I didn't times by 2 because I dealt with it here because I adjusted this based on the 3:2 ratio. So I looked at this to work out the number of moles over here. It's 2/3 of it. So I've dealt with the 2. Now it's just timesing it by the MR. So it's a little bit of a tricky one, but I'll explain it separately if necessary. So there you go. That makes sense, right? Hopefully that makes sense, right? So as I said, it's good that I made that mistake at the beginning because, as I said, in chemistry, officially, the mass of the left-hand side should equal the mass on the right-hand side. However, if something doesn't fully react, then you're not going to get as much mass. And that is precisely what happened over here. We got 53.4 rather than 56 point something. Right, let me move on to the final part. If you are in year 9 and you're still here, this bit isn't going to be relevant for a while, so I wouldn't stress about it. We are going to go through something called reversible reactions. A reversible reaction in chemistry is as it sounds, really. It can go backwards. And the symbol for a reversible reaction, so normally in a chemical equation, we have an arrow pointing from left to right. A reversible reaction symbol looks a bit like this. It's supposed to be 2 arrows and then with like the ends cut off. So that's what it's supposed to be. Make that a bit smaller. Right, so there is a symbol for a reversible reaction. Some reactions are reversible, and I'm just going to pick one, which is a common one, which you, depending on whether you end up doing triple science or what, you need to know a little bit more about it. And that is something called the Haber process, where we combine nitrogen and hydrogen to make ammonia. I'm going to balance this equation by putting a 3 there and putting a 2 here. So this reversible reaction is used to produce something called ammonia. Ammonia is what we use for, amongst other things, fertilizer for plants, and it probably in like bleach and stuff or cleaning products, I think. Now, the problem with a reversible reaction, or at least let me explain how a reversible reaction just means that these two can react together to turn into this, and this can decompose back into those two. So it literally is a circular idea where this can turn into that, and this can turn into that, and then this can turn into that, and you can continue going. Now, every reversible reaction, when you do it in a closed container, this is my illustration of a closed container, or closed, reaches something called equilibrium. Let me try to explain that using a different scenario, okay? So imagine I've got these things. This is, if I've ever taught anybody this, you'll remember this, and you'll be sick of it. But Imagine these blue and green things are reacting together. Okay. And remember how things react together in chemistry. You can't see this happening, but these particles are colliding with those particles. There's collisions going on. Okay. When they collide together, they form a new thing, a product. Okay. And so essentially, let's think of it as them. So I'm going to make this reaction A plus B reacting together reversibly to make C and D. So imagine these are C and D. Okay, so I'm going to use different colors in a minute. So if this particle hits that one and they join together, what happens is that we get some of C and D. And then when this one hits this one, we get some more of C and D. However, at the same time, C and D, because it's reversible, start colliding with each other. So this collides with that and turns back into A and B. That was A and B. Okay, so constantly what's happening here is that these are hitting each other, making some of these, but then these are hitting each other and going backwards to make some of these. So that's why it's called reversible. But let me slow this down a little bit. If you remember from the topic of rates of reaction, and this is actually a topic, this is within the topic of rates of reaction, where you can speed up a chemical reaction if there are lots and lots of collisions going on. If you the more frequent collisions, the faster the rate of a reaction. Now, if we just focus on these things now, because there's so many blue ones, and so many green ones, there are going to be lots and lots of collisions amongst these two. So they will be hitting each other a lot and quickly reacting to form the products. Okay, they'll be quickly reacting to form the products. And then gradually, as the numbers of these die down, remember, every time they hit each other and they react, they turn into something else. So the amounts of A and B over time, as with any chemical reaction, it slows down because it starts off with loads of stuff and then it gradually slows down. So if I drew a graph, I appreciate graphs can be irritating, but if I drew a graph of how fast this reaction is going over time, it would start off really fast and gradually be slowing down because now the number of collisions will be a lot less frequent, right? So it won't be reacting as quickly because there'll be less frequent collisions here. If we now move on to the other side, at the beginning, there were none of these or very few of these, right? A of C and D because we hadn't made any of them. The color's not changing. And so these were hitting each other, but very infrequently because there weren't that many of them. So the rate of the reaction backwards, that's backwards and this is forwards, was very slow. It was down here. There's the rate and there's time. Okay, so it was really, really slow reaction. However, as time went on, more of these were suddenly being produced, which means that they were now colliding with each other more frequently. And so this reaction starts to get faster. But quickly, once they start hitting each other and disappearing, it starts to slow down again. Meanwhile, as these were reacting together, we started to increase the numbers of the other side, which means that they started hitting each other more. And the speed of this reaction went up. You can hopefully see where this is going, right? Which is that what happens is the rate of the reaction in one direction kind of does this before it sort of levels out. And similarly, the rate of the backward reaction sort of goes up and down initially before it reaches a point where the speed at which these are turning into this is the same as the speed at which these are turning into that. And at that point, the amounts of these things, just making a little bit more, stop changing. So whatever we've got here will stay the same because the reaction, these are turning into these as quickly as these are turning into these. So you reach this thing called equilibrium where the speed of the reaction going forwards is the same as the speed of the reactions going backwards. And so everything stops changing, right? Nothing, we don't increase the amount we're producing. Whatever we've got of this A and B is the same as stays fixed, and whatever we've got of C and D stays fixed. That doesn't mean that the amounts are equal, just to be clear. Whatever the amounts are, just stop changing. So you could have more of one side than the other. So people get that wrong when I ask them about what equilibrium is. They say something like both sides are equal or something vaguely rubbish like that. It is equilibrium is when the speed of the reaction going forwards is the same as the speed of the reaction going backwards. That's what equilibrium is, okay? And so same in this ammonia Haber process thing that I said. These two will be reacting together to make this, but then this will be, I know it can't react with anything, but something will be happening. It decomposes to turn back into the the left-hand side. And at some point, we will reach an equilibrium where the speed at which we're turning this into this is the same as the speed at which we're turning into that, at which point, let's say we've got this much nitrogen and this much hydrogen and this much ammonia. Okay, the amounts of both sides stop changing. Okay, so there is no change to the amount of stuff on the left-hand side and the amount of stuff on the right-hand side. And there's no way of, well, it stops changing. So we can't now suddenly get more ammonia easily. But we want to. The whole point of this reaction, in this case, and any chemical reaction, is you're trying to make something, aren't you? And you ideally want to make as much of it as possible. The problem with a reversible reaction is that a lot of the stuff that you wanted to make has turned back into the stuff you started with, and it's a complete like pointless exercise where you're trying to make more of this stuff, but you can't. And so there is a way. And in reversible reactions that are at equilibrium, there are two main, was third really, but two main specific conditions that I can change. If I have started this reaction and reached this point where nothing's changing now, we've reached equilibrium, the reaction's still going on, just to be clear. This is still happening, it's turning into this, but this is turning back into that just as quickly. So nothing overall is changing. We are sort of reached this stalemate or equilibrium position where nothing is changing. If I want to now do something so that I get more of one side than the other, there are two conditions I can change. I can do something with the temperature. Changing the temperature can result in more of one side than the other, depending on something. And I can also change the pressure of this reaction. Again, changing the pressure can result in more of one side than another side. But again, you need to know, and this is where the important bit is, you need to know what actually happens. So when you increase the temperature, which side does it go to? Does it go more to the, do we get more of this side? Or do we get more of the other side? Or if I change the pressure, which side do we get more of? I'm going to tell you the answer now. You won't necessarily remember it immediately, but we'll go with it. And this is the answer. Any reversible reaction is endothermic in one direction and exothermic in the other direction. This particular reaction, usually you will get told this in the exam, but this particular reaction is exothermic when it goes in that direction. That means as nitrogen and hydrogen turn into ammonia, energy is released. But when ammonia is turned into nitrogen and hydrogen, it takes in energy, so it's endothermic. Every reversible reaction is endothermic in one direction and exothermic in the other direction. And you'll be told this most of the time, okay? Now, once you know that, which way is endo, which way is exo, then you need to know what happens if you change the temperature. If you increase the temperature of a reversible reaction that's at equilibrium, like this one, if you increase the temperature, you get more of the endothermic side. So for this reaction, if I made it really, really, really hot, what would happen is we'd take in all of that heat and we would turn it into more nitrogen and hydrogen. So we would end up for a while with more of these two. It would then reach equilibrium again because it always balances out. But for a while, you would produce more of that side, okay, if you increase the temperature. So the rule is if you increase the temperature when we've got a reversible reaction, you get more of the side that's the endothermic side. Okay, if it had been the endothermic the other way, then we would have got more of this side. But for this reaction, it's endothermic to the left and exothermic to the right. Again, you'll be told it each time. So it's that side you get more of. So in this reaction, if I wanted to make more ammonia, if I wanted more ammonia, then increasing the temperature is a bad idea. Because if I increase the temperature, I get more of the wrong side and less of the right side. So what you would need to do in this case is use a low temperature, as low as possible. The lower the temperature you use, the more you will get of, let's do this, the more you will get of this side. Okay, so the lower the temperature, the more you'll get of the exothermic side. The higher the temperature, the more you get of the endothermic side. And there's a subsequent issue with that, as you hopefully know, is that if I said to you, oh, great, all you need to do to get loads and loads of ammonia in this reaction so you can sell it and make loads of money selling bleach, is use a really low temperature and you'll produce loads of it. The problem with a low temperature with any reaction, as you hopefully know, is that the reaction happens very slowly. You have a very slow reaction. So whilst you'll get lots of this, it might take a really long time to do it. So commercially speaking, it might not be a very profitable thing. If it fine, you get loads of this, but if it takes 20 years to get loads of it, then what's the point? So you usually compromise and you use a slightly higher temperature so it goes a bit faster, okay, for this very specific reaction. But I'm going into more detail than necessary. I think for now, if you increase the temperature, you get more of the endothermic side, and that will be told to you in the question most of the time. Um, the other condition, the last thing I will do, is say what happens when you change the pressure of a reversible reaction at equilibrium. Well, if you change the pressure, then you have to do some counting. What you need to do, you will always be given this balanced equation. I've deliberately balanced it at the beginning when I wrote it down. This balanced equation includes these big numbers. There's a one there. I know there's not actually a one there, but pretend there's a one there. There's a three here, and there's two over here. What you do is you count how many molecules you've got on each side. And by molecules, I just mean these big numbers. Count the big numbers. On the left-hand side, we have four in total. On the right-hand side, we have two in total. If you increase the pressure of a reversible reaction, then you get more of the side which has fewer molecules. Okay, you don't have to understand why, but the side that has fewer, so the smaller number, is the side you would get more of if you increase the pressure. So if you increase the pressure of this reaction, because there are fewer molecules on the right-hand side, 2 compared to 4, you're going to get more yield of ammonia. And that will be wonderful because that is the thing that you're trying to make. So increasing the pressure here results in more of that side. Increasing the temperature here results in more of the other side because it's endothermic that way. That's it. And that you should be able to now apply that to any reversible reaction. So all you need to do is know which way is endothermic, which way is exothermic. It usually will hint at it in the question, if not explicitly tell you. And then it might say, what happens if you increase the temperature? Well, you just get more of whichever the endothermic direction is. That's the side you get more of. Then it may say, what happens if you increase the pressure? You'll be given the reaction, whatever it is. You count how many are on the left-hand side, count how many on the right-hand side. The side with fewer is the side we move to or we get more of if the pressure is increased. And I think, let me see if anybody else has said anything in the meantime. Which unit is this? It's later. It is in AQA. Oh, you want to tell me what unit is this? This is towards the end, isn't it? Top if you five a five. Oh, I can't remember. Let me find it now. I don't know the numbers. Six, I think it is. I'll check it now and then we'll finish. If you have any other questions, as I say, I will try to do some extra stuff in the over Easter. It just depends on our intensive courses, things which you're going to send an email about tomorrow to Newcastle people. If I'm doing those, then it's a bit tricky. If I'm not doing those, then I have a bit of time. So combined, separate is the same thing. Wonderful. Okay. So just final thing, and then I'll let you go. It is specifically that topic that I just did is in topic 6. So there's rates of reaction, which you often do. I mean, often you sometimes do this earlier on in your life, like how temperature speeds up a reaction or concentration or catalyst. But then the second part of the same topic is called reversible reaction and Le Chatelier's principle. Le Chatelier's principle is the thing I just said, which is that when you change the temperature, you things happen. When you change the pressure, things happen. And that is quite literally all of it. Right. Hopefully that was helpful. I will stop there and we will do this again next Wednesday. If not, we will also do, not if not, we will do it, but we may have additional things over your holiday period, depending on my schedule. So just